Okay, so for those watching the recording, sorry about that. I missed the first couple of slides by accident, but we're recording now. Okay, so as I said, templates are a way to reduce this duplicate code. Write code once that works for many data types. And we can template functions in C++, classes, and a few other things that are not as important, which we won't talk about. The textbook that you used for ECE 244, Chapter 17 is all about templates in C++, so it's a good reference if you want to go read more about this. Okay, so let's talk about function templates first. So here's a simple function. It's going to swap two values. So we pass in two integers, a and b, and we're going to swap their value. So classic way to do that, we basically declare a temporary variable, set it equal to a, then we set a equal to b, and finally we set b equal to temporary variable. So pretty easy. Here's a quick question to see how much people remember from 244. Why do we have these funny ampersands? So you just type in the chat or unmute yourself, whatever you prefer. What are these ampersands doing? Why do we need them? Yeah, so those ampersands mean pass by reference, which means that the compiler doesn't pass the value of that variable. It actually passes behind the scenes. What it's really doing is passing a pointer to it. So you don't have to worry about that. It's doing it all for you. But that allows it to, this routine is changing the actual variable, not a copy of it, which is what we want. A swap function that swap just copies would not be very useful. Okay, so that's great. You all did well on that question. You would have done well on the exam, I'm sure, if it had happened. Now we might want to swap more than just integers. So I've written this integer swap function, and I find I need to swap doubles too. So I write the function again, and you'll notice that this swap function is actually identical to what I just wrote. The only thing I changed is the integer declaration changed to a double. So this makes me feel a little bit sad, right? I don't feel like I'm making the best use of my time. I'm writing the same code twice. And if I have many types that I might want to swap, I might write this code over and over again. That's kind of a pain. Let me ask you a quick question. Is this okay? I'm going to do a quick poll here. Just again, quick 244 review. Is this going to work? And let's do a quick poll. See if I can make the poll button work now. So just click on, is this going to work or not? Will these two functions compile? We got two functions with the same name. Is that okay or not? Okay, so I'm going to give you just another 20 seconds or so. This is one where you either have an opinion about it or you don't. There's not much more you can do. So you have the last 10 seconds to get your vote in, then I'm going to end the poll. All right, so let's see what people said. Yeah, and most of the class got this right. This will compile. So 81% of you said it'll compile, it'll work fine. And it's because in C++ we allow function overloading. So the compiler is smart enough to realize that even though these two functions have the same name, they take different inputs, it's actually going to make you two different versions of the function when it compiles your code. That's nice. We can use the same name more than once because it's going to be easier to remember than how to swap two numbers. We can just call swap all the time. But we did still have to write two versions of this function, and they're almost identical. So I feel kind of sad about it. And I see a few of you are saying it's too soon after the holidays for such questions, and I hear you. It is still pretty soon, but most of you got it right anyway. Okay, so let me stop sharing this. Okay, so that all works. With what you know in C++ right now, if you wanted to write swap for a whole bunch of different types, so we can always count on using it, we're going to have to write a lot of code. We're going to have to write swap many times for different types. And there are some significant negatives of that. Well, obviously we just have to write more code, so that takes longer. It's also error prone. We're copying the code, we're changing the type, we might make a mistake. Swap is pretty simple, so maybe we won't make a mistake, but if this function was a little more complicated, there's more probability that we make a mistake when we're copying this code and changing the types. If we later find a bug, we'd have to go fix that bug in many places, which again is going to hurt our productivity. So second option, what you're going to be able to do after this lecture is write a template where the type can change. And the advantages are we have to write less code, and it's going to be more general. It'll support all the types essentially that make sense. You'll see what I mean by that in another few slides. So it's going to support more types than we would probably get just by writing many swap functions, because we're going to get bored. And the template could actually do even types we haven't written yet. Negatives, there's not much of a negative to writing templates. It does make the compiler have to do more work, because the compiler has to analyze your code, see what are all the types that you call this function with, and build a version of the function for each of those types. It makes the compiler take a little longer. Nowadays, people aren't very worried about compile time. Computers are fast. This is not a really big deal. They worry more about how long it takes to write the program than how long it takes to compile it. So yeah, I see a question in the chat. Could we use the auto keyword? And no. So the auto keyword is different. We're going to talk about it. I don't have any examples with the auto keyword this week, but next week I'll have some. Auto is basically just a convenience. When you declare a variable and immediately assign something to it, so you say int I equals 2, and therefore the compiler can immediately figure out, well, this has to be an integer based on what you assign to it, then you can skip the declaration of type and just say auto. You can say, you should be able to figure this out. That is different than templates. Templates is you're making a recipe that works for any type. Auto is just a convenience of, you say the compiler should be able to figure out the type here. It's unambiguous. I'm not going to write the type. I'll just say auto. Does that answer your question? Okay. Okay, so how do we write a function template? So there are a few pieces. So the first thing is we have to tell the compiler that we're about to write some templated code that works for multiple types. And we do that with what's called a template prefix. That's what this whole thing is. So it's this funny looking line. It says template. And in C++, when you're basically declaring what's called a type variable, or a type name, more specifically, we use these angle brackets to say that I'm about to tell you about a type. So I'm saying what comes after is a template, it's a recipe for functions, and it's a recipe that works for a type, and I'm going to name that type, okay? And now in the actual function, wherever I used to use int or double, I now use this name. I declared this name type, and I can use it as essentially a placeholder. It's like some type. I don't know what it is yet, right? It works for all sorts of different types. I need to give it a name so I can refer to it in the code. So I've chosen to call this type. I don't have to call it type. I could have called it something else. So everything in purple is a keyword. You have to use those exact words. Type is a common name that you would use for this type that you can essentially select, but it doesn't have to be that name. It could be anything you want. Okay, so the code basically after this template prefix looks the same as before, except instead of saying int or double, I just say type. And when we use this function, the compiler will actually make a version with the proper type. Okay, so what will this work for? If we look at what is the code inside the body of this function, we see we only use one operator and we use no function calls. So we use the operator equals, the assignment operator. That's the only thing we use. We use it here, here, here. So we use it 3 times and we use nothing else. That means that this recipe, this template for swap, all it needs to work is that there is a operator equal defined for the type that you pass in. And most things have operator equal defined. So it's defined for integers, it's defined for doubles, and if you make your own class, you're almost always going to define it too. So this swap function is going to work for almost anything. If you happen to make a class that doesn't have operator equal defined, well then it won't work. The compiler, if you try to use it, it will give you an error. It'll say, I can't use this recipe because the type that you're trying to use it with does not have the required features, doesn't have this operator equal. Does that make sense? Not all types. So the question is, do all types have operator equal? I mean, the vast majority do, but no, you can define types that don't have operator equal. But everything built in, like int, double, floats, all have operator equal. and strings, which is not built in but is a class, also has operator equal. So the vast majority of classes and types have operator equal. There are some where people decide they don't want to allow people to copy or assign values, and they just won't define it. So let's see. So in a word, we must use, if you use something in a template, then the template must have that thing to make it work. Yeah, that's exactly it. Okay, so Sage is saying, so the rule is you look through all the code in this templated function, and you see what are all the things it does. And to use that templated function, that recipe, every operation you use in the recipe must exist for the type you're trying to use it with. Okay, so let's go into how we use it. So that's how you write the templated function. So a lot like a regular function with this extra feature of a parameterized type. How do we use it? So we basically use it the same way we use any other function. So you've actually used in the standard library already some templated functions, you didn't know it. Okay, so using them is really simple. So let's walk through this code. So I've got a couple of integers, I and j. Initially they're 5 and 9 respectively. And then I call the swap routine. And I just call it like any other function. Doesn't matter that it's a templated function. The compiler looks at the type of I, looks at the type of j, says, they're both integers. I need swap of integers. Okay, does that recipe work? The recipe does work for integers because we have operator equal defined, so it compiles. Okay, and after the swap, they would be flipped. Okay, then I make a couple of doubles. So declare a couple of double variables x and y. I call swap again. Now in this case, I've decided to say which version of swap I want. So I've said I want this version of swap for double. And the compiler will say, oh, that's okay. X and Y are double. This matches. I can use that. So it's fine. It'll make me a double version. And these two variables will be swapped. I don't have to do this. Like I could just leave this double out. And in fact, that's normally what you'll do. I'm basically just showing you that it is an option to say which version of swap you want. But you don't have to do that. And to be honest, in most code, normally you don't bother, right? You just say, give me swap. You figure it out. Because the compiler, if it doesn't like what you put in this angle brackets, it doesn't make sense, doesn't match the type, it's going to give you an error. So generally, we're not going to bother doing this because we're doing more typing. And if we make a mistake, the compiler will give us an error. If we don't type that in, then the compiler will just do it all for us. So that sounds nicer. That's a good question by Jazz Newer. What if I and j were of different types? So it's a great question. If we go back to our recipe, we said there is one type, we gave it a name type, and A and B are both of that same type. So if the two variables that go in are not the same type, it does not match the recipe. And the compiler will not compile it. It will give us an error message because it's going to say, I don't have a recipe for that. I have a recipe for making a function called swap that takes in two variables of the same type. And you didn't give me that. You gave me two variables of different type, so I can't do that. And you will get an error at compile time, which is it's better to get errors at compile time than runtime, so that's good. And then Rohan has also a good question. So at compilation, will every type that uses this function have its own function made? And that's exactly right. So templates aren't magic. The compiler is basically doing essentially the cut and paste coding that you would do. Let's say I have 50 different types that use this swap function. The compiler goes through all your code, figures out what are all those 50 types, and it basically generates 50 functions named swap, which will all work because of function overloading. It generates essentially the identical object or machine code, the stuff that actually runs, as you would get if you actually manually cut and pasted this swap function 50 times, pasted in the types 50 times, and then compiled all that. It just does all that for you. Does that make sense? Let's see. So the question is, why use templates for short codes? Because I don't want to write those 50 functions, right? So if I write swap and then the compiler figures out I need it with 50 different types, I wrote swap once. If I have to go through all my code, use the swap function, and I need to write it myself for 50 times, I have to cut and paste and modify that code 50 times. That is a lot more work, okay? Let's see, here's another question. How does the compiler figure out all the types? It looks through your code. So the compiler is compiling your code, it's going through it, it sees every call you make to swap, it knows all the types that are being used with swap. And yeah, these are all very good questions. So a question from Ron, can you make exceptions for specific types? Yeah, so this is now more advanced. I'm not going to go through it, but part of the reason we have this notation is it's more for when you're writing the function. What I wrote here for swap is I wrote one recipe that works for all types. You can actually, if you want to get fancier, write versions for specific types. I'm not going to go over that, but that basically lets you maybe optimize certain versions. Maybe you got a special trick for your swap of strings and you're going to make a different recipe for them. You can actually do that using a notation that's kind of like this. Not going to show you how to do that. It's actually done sometimes by library developers. How you use the function is still the same. Okay, so you just do that. It'll always work. Okay. Another question. So good question from Narendra. So does the function do implicit casting? So there are some conversions, right, from integers to doubles. Does the compiler use any of those conversions? It will not. Okay, so because templates work for any type, the creators of C++, I think, very wisely decided that if they allow conversions before while they're trying to figure out what function are you making, what types are going in, that no one will be able to figure out what's going on. Okay, you have a template that works for all sorts of types, and then you have conversions between all sorts of types. And if you say I might apply some conversions and then I might try to make the template, it's just impossible to figure out what's going on. So what they said is when you use a templated function, you must match the types that it expects. Okay, and the only thing our templated swap expects is just one type. That's all. Okay, it's happy as well with any type that has the deep copy operator, or has the operator equal operator, sorry, as long as it's just one type. It will not do conversions. So you pass in ints, it's trying to make the function with ints. You pass in doubles, it's trying to make the function with doubles. It will not do any conversions because no one would be able to figure out what the heck's going on. It's too dangerous. Okay. So anyway, so those are very good questions. So let's go on. I'm going to look at this for a second. I'm going to launch another poll. So we just went through a whole bunch of rules of what will compile and what will not compile. And you can get, I'm going to show you a demo of this at the end of this hour. But basically, when the compiler can't figure out how to use templates, you get an error message, and at first it might be a little hard to interpret. So we're going to look at this code and just say, well, which of these are going to work and which ones wouldn't work? So you get a little bit of expertise in what are the restrictions. Okay, so let me start a poll here. I'll give you a couple minutes to look at that and just fill in which of these lines you think will compile and which won't, given all these types and these calls to swap. Okay, so now as they're doing that, yeah, Hitsarth, that's a good question. You're basically asking, could I write a swap that takes two different types? You could. So if you wrote a swap function that took two different types, then the compiler would be happy to use it. Now, it is harder for you to write that recipe because you kind of go, well, what does that mean? Like, what am I doing exactly with these two different types? Am I setting them equal to each other? So it may not be meaningful to make a swap operator for two different types, but if you can think of a meaning, yes, you can write a template that takes two types and it'll work then. Is it possible to nest templates? Essentially, yes. So a templated function that you could call another templated function. And in fact, you've already done this probably in your code, you just didn't know it. Because when you're calling templated functions, the code you write is the same. So some of the library functions you've been calling are templated, and they themselves can call templated functions. It's all fine. But again, for functions, the code you write, usually you don't bother saying which version you want. So it's kind of even hard to tell by reading the code that you're using templates. Okay, so Linda has a question of if you make your own variable type but don't overload operator equals, so you get the default one and it's a shallow copy, will it work? Yeah, it'll compile. The compiler doesn't evaluate, is this operator equal what you want? If it exists, it's happy. If all you needed was the automatically like a shallow operator equal, the default one, then it works in the way you wanted. If that's not what you wanted, then it'll still compile, but won't do exactly what you wanted, and you have to go write a better operator equal. So it's kind of on you. And that's not really any different with templates versus without. If you write a class and and the operator equal doesn't do what you want, then your class is not very good. Okay, so I'm going to give you another few seconds to fill this in, and then I'll show the results. Okay, so I'm going to show you the results, and let's see, let's go through these. Okay, so the first line. So we've got a character M, character N, swap of M, comma N, and 95% of people said it would compile, and that's exactly right. Okay, so we have two different variables, they're both the same type, that matches. Characters do have the assignment operator defined, it's all fine. Okay, next one. So swap I, comma N. So I is an integer, and N is a character. So 17% of people said it would compile, 83% said it wouldn't, and it won't compile. So most of the class got this right. It won't compile because the types aren't the same. The swap we wrote takes two variables of the same type. These are not the same type. Now you could say, well, wait a second, can't I convert a character to an integer? And you can, but again, C++ will not do any automatic conversions when it's trying to match a template. And that's because it would cause chaos. There would just be too many possibilities of how are we trying to match this template? What are we doing? People couldn't figure out what's going on. So that's much worse than just the compiler saying, I don't like this, you got to give me more information. So it won't work. Okay, swap of double of ij. So in this case, we have asked for a specific, I'm just going to scroll down here so I can see more of the pool. We've asked for a specific version of the swap function. So we asked for double, and the variables we're passing in are actually integers. So this won't work. It would have worked if we actually just didn't bother putting the double in. So we probably shouldn't have done that. So I'm showing you this so you know the rules, but I would recommend you just don't bother doing this. You just ask for the function. Don't put any of these templates in. Okay, then we can say swap, and I'm saying I want the integer version for sure, but now we've got I and j, which are integers, and 97% of people said that'll compile, and yeah, that'll compile. And the last one, we got swap of character. So we're saying, give me the character version. We pass in x and y, which are doubles. And let's see what people said on this one. Yeah, 88% of people said it won't compile, and it won't. If I got rid of this character, so again, if I hadn't said that, it would be fine, because it's two doubles. But because I said I want the character version, the compiler is going to say, well, it doesn't make sense. Okay, so yeah, so well done. People got that quite well. Okay, so I'm going to have you go to this online IDE and implement in breakout rooms. So I'll put you in pairs. Implement together a templated minimum function. Okay, so how do we write this? The first thing we do in a template function is we have this template prefix. So we say the code that comes after is going to be templated. It's a recipe, and the recipe is for some type, and I'm going to call that type. So that's the first thing. What should my arguments be? So I want to pass in two things. Let's say A and B. What is the type of A and B? So you just type it in the chat if you know what the type of A and B should be. Somebody must know. Yeah, it's just type. Okay, so it's just that easy. I named my type variable type. I just say type A, type B. That's my recipe. Okay, what am I going to return? I'm trying to return the minimum of those two things. Yeah, it's again going to be type. Okay, so that much you got. Now you just have to go and implement the function body, which isn't going to be very long. So I'm going to put you in breakout rooms. I encourage you, talk to each other, turn on your cameras if at all possible, because this whole being online in a pandemic is obviously isolating. So this is a chance to see at least a two-dimensional representation of somebody and chat with them for a few moments. So let me put you in breakout rooms, take a crack at this. So, and let's see, it's been 35 breakout rooms. Okay, welcome back, everybody. How'd it go? Type in the chat. Were you able to finish it in that amount of time? So just type a yes or no. Get a sense of how fast that was. Okay, sounds good. Sounds like it was enough time. That's great. Okay, so what does the function look like? So I have to go look at what version we have on the IDE. It may not have been exactly this one, but this is one way to implement that templated minimum function. So we can say if A is less than B, return A, otherwise return B. Okay. So just type this in the chat. When will this work? So what are the restrictions on A and B in order for us to actually use this template, be able to call this minimum? Yeah, Rohan's right. So it's when A and B can be compared. The operator less than must exist. And they also, Linda's also right, they also must be of the same type. Okay, there's two requirements. We said we got one type, so they must both be of the same type. And we use this operator, so it must exist. We don't use anything else, nothing else, no other restrictions. Okay, so we just talked about that. We don't need operator equal now, right? We didn't use it, doesn't have to exist. We only need what the recipe uses to exist. And there could be some types where it's not defined. Okay, so that was function templates, and that's all there is to it. You've been using function templates when you use the standard library without knowing it, and you can keep doing that. Now let's go on to class templates. Okay, so what can you template inside of a class? Well, functions, and basically we do that the exact way we just looked at, so you kind of know how to do that already. But we can also template the data. And I'm going to give you a few examples of let's see, I see a question from Yusef. We need operator equal for exercise 1 because we assigned to it. Let's see. In this implementation, I never use operator equal. You don't actually see any equality, any assignment, therefore it's not used. Okay. Yeah, so in the code board, I'm going to go look at the code board code. I heard this from the tutorial on Monday. I haven't gotten to it. So in the code board code, yeah, it is slightly different. So if it uses the operator equal, then it's different. It needs that to exist. Okay, so I'm going to give you a few examples of what could you do with a templated class. So let's take this one. So you can make templates of all sorts of different classes. You learned how to do linked lists in ECE 244, but when you made a linked list, you always made it for a specific type. Integers or double precision or resistors or something. And that can get kind of tedious. So a templated linked list, we could just make a linked list recipe, and then we could use it with any kind of data that we want to store. We could do the same thing for a binary search tree. We could do the same thing for some kind of more fancy array class. So this feature is really useful in classes where you can make basic classes like linked lists and make them work for any data rather than writing them over and over and over again. Okay, so let me give you a simple example of a templated class. This is simpler than a linked list or a binary search tree, but it's actually still useful. So it's often useful to store two pieces of data together. And the number one reason you would do this is what are called key value pairs. So in ECE 244, you learned about binary search trees. And in those, the nodes store, so every node in that tree stores two things, a key and usually a value. Okay, so it has to store at least a key, but usually there's also a value. So for example, we could have a key that is of type standard string as the name, and we could have a value, which is what you're trying to find, and that might be an integer student number. So we can make a binary search tree now where we can give student names and it can very rapidly tell us the student number. And again, this is like a key, what do we use to access the binary search tree? String, and the value, in this case, data we can get out of it is an integer. But you can do this with all sorts of things. There's no reason you'd say, well, you always use strings as your keys in binary search trees and you always have integers as the values you want to look up. No, you could have anything. But with binary search trees, you always have this notion of a key and a value, and the key is what you're sorting on. So to be able to group any arbitrary two pieces of data of any type into one object is useful. That's going to allow us, for example, to make more generic binary search trees. So that's what we're doing. We're going to write an object or a recipe, template to create objects that have just 2 data members, but those data members can be of any type. So we can't give them very descriptive names because this is very generic code. So we're just going to call the first data member first, and it's going to be of a type that we're going to call first T. And we're going to call the second data member second, and it's going to be a type second T. Okay? So these aren't great names if we knew more about the object, but we just don't know much about it. We're making a very generic recipe to just group 2 pieces of data together. What can we do with that? Well, if we had a binary search tree and wanted to insert some data in it, we now could basically insert an object of this type pair, and it's grouped the key and the value together. And we can do this for kind of anything. So that's kind of nice, very reusable. Okay, so hopefully I've motivated the pair class for you. It's a simple templated class, but it is actually useful. So it's an association of 2 different types of variables. And I already told you this, they're called first and second. And I can use this recipe to do different things. So if I basically say I want the first to be a string, I might make an object, and the second to be of type int. I might make an object with, apple and 4 in it. Or I could use that same recipe, but say now I want the first type to be double and the second type to be string. And I might make an object with the number 42 and the string 42 in it. I can use the same template recipe for both of these objects, even though they're storing different types of data. Let's see. Rohan's asking, what is the difference between a pair and a tuple? A tuple can store an arbitrarily long list of, it can be more than 2 things. So you'll find in the C++ standard library, there's a type called tuple, which you probably won't need to use, but it's like a generalization of pair. Instead of 2 data items, it can be a whole bunch of data items of different types. It turns out that pair is probably more important because it's used for this key value notation. Okay, so let's see how we're going to write this. So for our example pair class, the first thing we need to do is we need to have this template prefix again. So template prefix is just the word template, angle brackets to say I'm going to give you some type variables, so just names of the types. And we can have more than one type variable. So we basically make 2, first T and second T. So we're going to have 2 types that could be anything. So this class is not going to just have one type in it. Okay, and then we say this is for class pair. So this is the way we would normally write a class, except we've added this template prefix in front of it to say what we're giving you is a recipe, not just one class. Okay, and then we write the class as we normally would. I'm going to make some public functions, and I make a constructor. Okay, so the constructor basically will create an object, and I'm going to say this constructor takes 2 parameters. It takes a first val and a second val, and that's of type first T and second T. So all this says is it takes something of the first type and something of the second type, and it'll construct an object. So it's a recipe for making a constructor. We have some accessors. They look just like you normally write access functions, except we don't know the type. We just say these are setters. We're going to pass in some value we want to set first to, and that's going to be of type first T. Or we might pass in something to set the second value, and that'll be of type second T. Looks just like code you've already written, except it's generic. It's using these types. And then these are the actual get functions, same idea. We can, instead of saying int, they return ints or doubles or strings, we say, no, the get first returns something of type first T, and the get second returns something of type second T. And then we define our data. And our data, again, it's a recipe. So there's a data element that we're going to call first, and it is of type first T, and a data element we'll call second, that is of type second T. So, this class, if you were making a very specific class, these names are not very good, right? You shouldn't use names this generic. But for pair, these are good names because we're making a recipe that has to work for anything. So we can't use very explicit names. We just have to say things like first data element, second data elements. Let's see. There's some questions about for classes and functions, can we have more than one type? Yeah, we can pass in as many of these type names as we want, or define as many of these type names as we want. So for pair, we need 2. For swap, we needed 1. Okay, so does this make sense? Any questions on this so far? Syntax looks a little funny at first. It is a little bit harder to read templated code. So that's natural for everybody. Yeah, let's see. So Constructor is asking, do we use type, like these names, like first and second, when you want to be general purpose, and use specific types when you don't? And yeah, that's exactly right. So I could still use specific types inside these functions. I just didn't need to. So maybe you use some integers for like indices and so on. That's all fine. It's just wherever we want it to adapt for different types, we use these names instead of specific types. Okay, so kind of a note on how you do this. So generally in C++, we say, you put the definition of the class, like what are the member variables, how do you call the member functions, in the header file. But for any member function that's not really short, if it's really short, you can put it in the header file, but if it's not really short, you put the definition of the function, like the body of the function, in the .cpp file. For templates, the rules are a little different. Because the compiler has to be able to generate many different versions of the class I just wrote. Like that's really a recipe. It's not really a class. It's a recipe for making classes. It needs to have everything in the header file so that as it's scanning your C++ code, if it sees that you want a pair of string and int, it knows, okay, I better start making versions of pair for that. If it sees you want a pair of double and string, it says, okay, I better make another version. So you put all the code for templated classes in the header file, both the function declarations and the function bodies. That would be considered bad practice unless the functions are really short, if these were normal classes, but because of the way the compiler works is what you have to do for templates, okay? And I think I'll leave the question till the break on how would inheritance play in templated classes. They're kind of orthogonal is the short answer. And then there's a question of would things like pair auto work? You can't just use auto by it. Basically, no. You can't just say auto inside of a template when you're asking for a templated class, because you're not telling the compiler what kind you want. So you can't just say you auto. That doesn't really work. Okay, so I showed you the header file. I haven't shown you how the function bodies yet. So the function bodies still look basically normal. It's just the types use these type names. So for example, we had this constructor that we passed in 2 values, first val and second value, and we're supposed to make an object. We can do this just the way we normally would. We can say set the first member variable equal to first val, set the second equal to second val. So we're doing that by just calling their constructors, which is kind of the preferred way to write constructors. This is exactly what we would do for any normal type, so it's fine. The set first, where we're setting some, our internal private variable first, we just set it normally. We say we'll set first equal to what you passed in. The only thing that looks slightly different is we don't know its type. Its type is this type name. It's generic. So how do we use this pair? That's what the class looks like, or the recipe looks like. To use it, okay, we declare an object just like we normally would. So I'm declaring an object called pair1. I'm actually going to call it, I'm going to construct it. I'm not using the default constructor. I'm saying I want to call the constructor that with a value of 1 for the first parameter and 2.5 for the second parameter. And we have to say, well, what type of object is this? In C++, you always have to say the type when you declare a variable. Well, it's of type pair, but pair is not enough. Okay, pair is a recipe. We have to say what kind of pair. It's a pair with the first type being an int and the second type being a float. So this together is enough to say what kind of object do I want, and now we get an object with name pair1. And because of the way I define the class and what I'm trying to do, I also want to pass some numbers to the constructor. Okay, so what do we get after this is done? Well, we get an object in memory when we're running our program. So we would get an object called pair1. You would have an integer member variable called first and a floating point member variable called second, and they would be set to these values as the constructor requested. And if we go and we can go and basically do things like, print out their values and so on. Okay, this line is making a new object called exam. All right. It is also using the recipe pair, but it is a different kind of object. It's an object of class pair, but it's got a string for its first value, its first member variable, and a double for its second. So in memory, this line is going to create an object called exam. That object is different than this object pair 1. It's actually a different type. It's not the same size in memory. It doesn't have the same member variables. You could not say, you couldn't say something like this, pair 1 equals exam. That will not work because these are not the same type, right? They came from the same recipe, but they're not actually the same size. They don't have the same member variables. You can't do that, all right? But I can take exam and just use all my member functions on it normally. So I can print out the first, print out the second. I can update the entry for the second variable and so on. Does that make sense? Okay, so a couple questions here I see. There's a question, could the two member variables have the same type? And yeah, they could. So could I do basically a pair of int, comma int? That's fine, all right? We have to specify two types. There's nothing in our recipe to say they have to be different types. Perfectly fine for them to both be the same type. So that's gonna be fine. Okay, another question I see in the chat is, what's this std : mean? Okay, so in 244, generally you've been writing your programs where you do this at the top of your, whoops. Sorry, my writing is bad when I don't have the computer down. You've generally, near the top of your files, been doing this, using namespace std. That basically says any name you see in your program, like string, don't just look through my code, seeing if that name exists. Also look in the standard library, basically. Okay, look in what's called a namespace, and this is the standard library namespace. So go see if the name string exists there. So you can do that. If you do that, you don't need this std. It's generally considered somewhat better programming practice in C++ to actually be explicit about where is this name coming from. So the standard library, to make sure that its names don't conflict with any names you might use in your program, it's all put in something called a namespace. And if you want to access its names, like string, you actually have to say it's in the std namespace. This : is called the scope resolution operator. It just means look in the std namespace, look for something called string, right? So in this case, it's a class called string, and that exists, so this is going to compile. If you said using namespace std, then this becomes optional. Yeah, it's still fine to specify it, but basically the compiler will just look through all the names in the standard library automatically. As I said, it's considered somewhat, it's not terrible, but it's not considered the best practice because this is more explicit. It says it's in the standard library. Everybody reading your code knows exactly what you're trying to use. Let's see, does that make sense? Okay, so there's a question, you implement pair and header files. Yes, so the template code that I'm showing you that actually implements the pair class, you would write in a big header file or a couple header files, usually in one big header file. And let's see what are the questions. Yeah, so here's a key question. So Armin has a good point. For functions, I said you didn't have to do this, right? You could just call the function. You didn't have to say what the type was. For classes, when you're creating a new object, so I'm creating the object pair 1. Here I'm creating the object's exam. I have to say what the types are that are going into the template, into the recipe. So why do you think that is? I mean, the creators of C++ generally tried to save you from typing when they could. So if they don't need some information, they won't make you type it. This is not optional. You must do this. If you basically just say something like this, pair my val, and I call a constructor of 1, 2, that will not work. The compiler will say that is not actually the name of a class. I don't know how to do this, right? It will refuse to compile that. You have to put in these angle brackets and say what type. So why do you think that's the case? It's probably a good reason. Otherwise, the C++ creators would not have forced you to do all this typing. So any ideas? Why do we have to do this? Didn't have to do it for functions. Yes, so Mark's saying memory. So memory is part of it. We're creating an object. We actually need to know what size it is for the compiler to set aside the right amount of memory and so on. So that's part of it. Because it's a template class. Yeah, it is because it's a template class. So it's different than a template function. But I guess more fundamentally, why did the creators of the language say you have to do this? Right? So there's kind of two levels of understanding a language. There's like, well, it's just the rule. You just got to follow the rule. So the rule is, if it's a class, you do have to specify these. But then there's a deeper level where you think, well, why did they do that? Yeah, and so the answer is essentially what Constructor is saying, to make sure it gets the type right. Okay, so when you call a templated function, like swap, we did something like this. We said int I, comma j, for example. Oops, sorry, my writing is kind of messy. And then we said swap ij. So the compiler, you've already declared I and j. The compiler knows their types. It can look at these, it can figure them out, it can say, what do you mean? Which types? Here, we are declaring this variable. Nobody knows its type. We haven't said yet. So we say what its type is here. It's a pair with these type parameters. If we didn't set the type parameters, the compiler can't possibly know what do we mean. You want a pair, some variable called pair1. You want me to use the recipe pair, but you won't tell me which version of the recipe. And pair1 doesn't exist yet, so I can't look at pair1 to see, well, what is it? I don't know yet. It's just a name. So can't be done. So they say you have to tell us so that we can actually build the right thing and understand what you mean. There's no way for the compiler to figure it out. Okay. Sometimes people think a reasonable thing. They look at this and they say, wait a second, but you did call a constructor and you passed it an integer and a floating point number. Couldn't you figure it out from there? In some cases, maybe you could. Okay, if you only had one constructor and you knew that that constructor exactly matched the member variables, then the compiler could infer it. But it's common for classes to have many constructors, including default constructors, constructors to build in all sorts of different ways, constructors with 1 argument, 2 arguments, 3 arguments. So this would not be robust. In general, there's no way the compiler can figure out the types that you want inside of a templated class just by looking at the constructor. So the creators of C++, again, wisely just forbade this. They said, like, that is madness. You will tell us what you mean, because a programming language where nobody can say what the heck it's doing is not useful. Yeah, this is exactly what Simon said. We can have a constructor. One case would be a constructor with no arguments, which is common. And how could you possibly figure out what the types are inside the class given that? So you have to say it. It's fundamentally different. Okay, so let's see, we went through that. Any questions on that? Does it all make sense? Okay, looks like, can we take that as a yes? So I'm going to discard my annotation. I'm going to show you a quick demo. And unfortunately, I think ENC likes closing my connection. Let me reconnect here. Okay, so I'm on the UG machines using VNC. And most of you probably figured this out. You want to create a terminal. The easiest way to do it is applications make terminal. So I've already done that. I've opened up a couple terminals and I've got a little demo here. So I'm just using an editor that I like called VI. And this is a little program called mymax.cpp. So it's a small templated function. So templated function that computes the maximum of 2 variables, A and B. So if A is less than B, it returns B. Yeah, otherwise, it returns A. Works for, yeah, so it's pretty simple. And then I got a main function. And in my main function, I'm just going to call this max a few times. So I create a couple of doubles. I call max of those 2 values. Create a couple of integers. Call max of those 2 values. And then I do it with a constant. So I say the max of 2 and one of those integers, j. And then I just print out the results. Okay, so let me compile that. Actually, the first question, you can type this in the chat. Is this going to compile? Or is there going to be any error? So let's look at, yeah, and so Simon is saying, isn't 2 dot a float? And you're right. I didn't actually say here 2. I said 2 dot, which means a floating point number. Okay, so you guys are right to be kind of like a little worried about that. So you've got good eyes. So you're saying that line I don't think is going to compile, and you're actually exactly right. Okay, so I think in 244, did you guys use makefiles or did you just type G++? How did you compile your code for 244? Okay, you were given makefiles. Okay, so that's good. So you know make. So yeah, for any significant program, you don't actually sit there typing G++ and other commands to compile it. Because you're going to build it so many times, you create what's called a makefile. And the makefile is basically rules. If this file changes, like this CPP file that I've shown you, mymax.cpp, then here's what you should do. So in this case, you should run G++ with whatever options we specify in the makefile. And for bigger programs, that can save you a lot of compile time, because if you just change 1 or 2 files, it'll only compile those and then link them together. And it also makes things much more repeatable, because in larger programs, you usually wind up with many more commands to build them. Okay, so I'm just type make. And let's see, no makefile found. I think I'm in the wrong spot. So let's go into the correct directory. Okay, so just type make, and it built the program, or tried to build the program, and you guys were right. So it didn't compile, and let's see why. The reason I'm going through this is when you use templates, you can get longer error messages than you might be used to, but don't be intimidated by those. You just start at the top and start reading through them. Okay, so the makefile invoked G++, that's the rule that we wrote in here. We basically give it some options where we're saying, okay, turn on lots of warnings so it flags anything funny in your code. And this version is basically 0 and -G. This is good for debugging. This basically means compile the program in the simplest way you know how. So if I put it in a debugger, I can examine the names, I can see the names of variables. It works better in a debugger. And when I step through the code, it will go in exactly the order that I wrote it. Okay, so it would go, if you look over on the left, if I ran this in a debugger, I would see this line run, then this line, then this line, then this line, then this line. Okay, so that all looks good. So that's the way I've compiled the program when I just typed make, but it didn't work. It's saying in function main, line 17, there's an error. Okay, so let's go to 17. Okay, so now I'm on line 17. It's the one you guys said was kind of dodgy. And the error it's giving me is it says I can't find a matching function. So you call max, and I can't find a max function. And it tells you what version of max it's looking for. It's looking for a double and a reference to an integer, but it didn't find any matching function. Okay, that's the key message. Template error messages can get kind of long. So the first one is saying what really went wrong. The rest of this is kind of helpful hints. So the helpful hint here is it says, well, on line 4, so let's go to line 4, see where that, whoops, wrong window. This is line 4. It says on line 4, you had a function that almost matched. You had something called max that took some type, but it didn't work. And the reason it didn't work is that I figured out that there's this type parameter t, and it seems that I have to make it equal to both double and int, and I can't do that. It can't be 2 things. So this message says you are trying to use a template that takes 1 type and you try to use it with 2 different types. That's what it all means. When you get these error messages from templates, start at the top. That's the thing that didn't work. Then it gives you a bunch of helpful, what it thinks are helpful hints, and usually they are, of it almost matched this. Maybe that's what you wanted. Here's why it didn't match. So how do I fix this? I think you guys are probably already pretty close. You flagged this 2 dot is actually a double. If I get rid of the dot, it becomes an int. Oops. All right, so I just wrote that out again. I'm just going to make it again. Okay, now it works. Okay, and if I run it, it runs and gets the right answer. So it wasn't that hard to fix, but at first the error message might seem a bit confusing, especially because when you're looking at this, you might say, well, it's just 2 and an integer. 2 and an integer, why wouldn't that work? But again, C++ will not do any built-in conversions when it's matching a templated recipe. So to C++, that is, to a human, you look at it and you say, I know what to do. C++ says, I do not know what to do. I will not convert that double to an integer. I will just try to use the recipe. The recipe does not quite work, so you have to fix it. Okay, any questions on that? Okay, so let's take a break for a few minutes. Let's take a break for, we're running a few minutes behind. So how about we just break till 11:18? Okay, so not quite 11:20. And I'll still be online, so I'll answer questions. But feel free to go grab yourself a coffee or something. So let's see. So Maisie's got a question. Is it possible to specify more than one type in a template function? Yes. So just like I showed you for classes, I could specify here. I'll show you how you do it right now. So you go type name T1, comma type name T2, and now my function takes two types. I'm not doing anything with the second type, so I probably need to figure out what I'm going to do with the second type here. But that's how you do it. So it doesn't look very different. Let me fix this back up now. Okay, so let's reconvene in about 3 minutes. Go grab yourself a coffee if you like. Okay, we're back. So looks like a few more questions, but I'm just going to move on, and at the end of the session, if there are more questions, I'll just hang out and can answer them. So, okay, you know about templates now. Now we're going to talk about what do we do with these. And there's a very powerful library built into C++ called the Standard Template Library, or STL. So what are we going to talk about next? We're going to talk about why should you use STL, and then we're going to talk about one important class or templated class inside of STL called vector. How do you use it? How does it work? And then next week, we're going to talk about more classes that are inside STL. Okay, why would I use STL? Well, writing templates can actually be difficult. You saw that the syntax is a little more complicated, and writing a recipe that works for all sorts of different data types is somewhat harder than writing a class that only works for one data type. So writing templates takes some extra effort, but using templates does not. So using templates is pretty easy, and it allows you to use this powerful library. So you want to know how to use templates. It's not as important that you know actually how to write them. I just taught you that, but don't worry if you kind of go, that seems a little tricky. You don't have to write any templates in this course if you don't want to, but you are going to use templates. So for example, STL has a lot of features. It has templated functions for things like swap, sort. It has a templated class called pair. It has a templated function called min. So it actually has all the things that we just went over in the first example and lots more. And for some things like swap, it might not be that hard to write your own, but for functions like sort, the standard template library has very fast sorting routines. They work with any data type. It's much smarter to just use them than to go off and write your own. The main thing we're going to talk about in STL is the containers library. So the containers library are several basic fundamental data structures that are written using templates so that they work for any type. And that's very powerful. So one of them is called standard vector. Standard vector is basically a better array. So in my recommendation, both in this course and in your future programming careers, you basically, if you're writing in C++, you just switch to standard vectors as your default thing that you would use instead of using an array. They're like a better array. Other languages have similar concepts. So Java has something called an array list, which is the same thing as a vector. They just gave it a different name. And the containers library has more than just vectors in it. It also has, for example, linked lists. So it's called standard list. That's a doubly linked list, and it's a doubly linked list of anything. It can store any type. So in 244, in one of your labs, you wrote, I believe, a couple of linked lists. So a linked list for resistors, linked list for nodes. And probably as you're writing that, as you're writing the second linked list, you're thinking, this is getting a little boring, right? This code's looking awfully familiar. So you can stop doing that by just using standard list. You say, I want a list of resistors, give it to me. You don't have to write any code. So the data structures are templated. So these are classes. And when we create a variable of this type, we need to say what kind of vector or what kind of list we need. So I can, for example, say, give me a vector of doubles. It's like a better array that stores doubles, or give me a linked list of strings. And that's a linked list that stores strings. Okay, so let's talk more about vector, because that is one of the most useful container classes. So let's do that by just looking at a problem that is a bit tricky to solve with arrays, but vectors can solve it easy. So we want to read integers from a person who's typing in a keyboard, and we want to put them in an array. The reason we want to put them in an array is we're going to pass this on to the rest of our program, and arrays are really nice. They give you random access that's fast. You can get at the 5th entry, the 100th entry, the 1,000,000th entry in a vector in equal time. It's order 1 access, just by asking for that index. So arrays are very nice for their speed. So that's what we want, because that's what the rest of the program wants. But we don't know how many numbers this user is going to type. So the user is going to type some set of numbers, and then at the keyboard, end of file is you hit Control-D. If it was coming from a file, end of file is just whenever the file is empty. So we don't know how many numbers the person is going to type. So that's the challenge. We could allocate an array of size 5, and that would work for this case, but it's not going to work in the general case. So what do? We don't know how much storage we need until after the input is read. But the person's not going to go back and type it all again, right? We can't say type all the numbers once, we'll count them, then we'll make an array, and then go back and type them again. We can't do that. So what can we do? So there are ways you can solve this. So I see people saying, well, you could dynamically allocate an array. So yes, we could dynamically allocated array is going to be better than static. Static would mean we just fix it at compile time before we even run the program. But there's still a problem with a dynamically allocated array. Like, you have to say how many elements when you call new. How many elements do we ask for? 5 would work for this case, but the person might type 100 numbers. 100 would work for that case, but maybe this is coming, the person is sending it in from a file and there are 1,000,000 numbers. So they say, well, 1,000,000 numbers. But now if I could make the person send in 1,000,000,000 numbers. And if you start allocating arrays that big, you're going to run out of memory, or your program's going to be really slow for most people. So you're really overdoing it. You're just saying, I'll make giant arrays all over the place so I never run out of space. So that's also not a good solution. So Rohan's actually got a very good idea. So Rohan's saying, what if you start with a size and then double it every time you hit capacity? So that's actually what vector does. So Rohan has actually said the vector solution. And then we're going to go through how that works in more detail. And the nice thing about vectors is you don't have to write it yourself. It'll just do it for you. So another thing you could do, given that you know linked lists, is we could read this whole thing into a linked list, because linked lists, they're not as fast as arrays to get at the middle data. You have to traverse through the list, so that's kind of not as nice for the code that uses them. But the thing that is nice about linked lists is it's easy to add data at the end. So we could use a linked list. We just keep adding data. We don't need to know how much storage to allocate in advance. We just keep creating nodes and putting them in. And then once we're done reading the whole set of input into a linked list, we can basically go through the linked list, copy all the data. We can count how many items there are, allocate an array using new that's the right size, then go through the linked list and copy it all to that array, and then we could delete the linked list. And it would work. But it's a bit slower than we would like, because we had to create this whole linked list and go through it a couple of times. And we had to write a bunch more code than you probably want to write for something that seems kind of simple. So given what you know right now from 244, that's the way you would probably do it. Okay, we could use linked lists, but we're not. We're going to do Rohan's solution, which is essentially an array that grows. You could code that yourself, but if you just use vector, you get it all for free. So let's look at how it works. Okay, so a vector it's a lot like an array. Just think of it as a better array. So it has this operator square bracket, like the indexing operator. So we can use that like this. I've got some variable I've declared called my vector. I could say I want the value at index 42, and maybe I've stored integers, so we'll capture that in some integer. That's fine. So it looks just like you would use an array. But you can do this, which you can't do with an array. You can take the same object, my vector. I'm going to call a member function that vector provides called pushback. So whenever I call a member function, it's always the same: object name, dot, and then member function name. In this member function, I basically say I want to add to the end of the vector this entry. Okay, so my vector in this example is storing integers. So I'm basically saying make one new element in the vector and store the number 5128 in it. And that's all done by this pushback function. We can modify existing elements. So I can say index 42 in my vector should now store the number 64. Looks just like an array. So we're using this square bracket operator again. And a vector knows its size. So when you used arrays in what are called C-style arrays. So the arrays you used in 244 are generally called C-style arrays because they're really inherited from C. And that's fine, but vectors are kind of nicer. So vectors have this size member function, which tells you how many things there are. And it's just like an array. A vector that has, if size returns 3, it means that index 0, 1, and 2 all exist. Just like an array that has 3 elements, you would say those are index 0, 1, and 2. But it's a bit nice that a vector knows its own size, because you probably found with these C-style arrays, you usually had the array itself and they had some counter that stored how many entries are in it. A vector just groups those together. There's no insert at front function. I have to go, it's not commonly used with vectors. So this STL does have a push front function, but for vectors, it's not efficient. So I believe it doesn't exist for vectors, because one of the things that STL tends to do is operations that are inefficient, they just do not provide on a particular container so that you don't write really slow code. Instead, the compiler says that function doesn't exist for that object, and that's a hint you should go look at. That doesn't seem like a smart thing to do, right? Because it would be slow. Does that make sense? Let's see. And I'm going to defer. Actually, you have a very good question. I'm going to defer that until a little later in the lecture. So remember that question, and I'm going to come back to it. Okay? All right. So hopefully that shows you, the basics of what a vector is. It's like a better array. We're going to look at how we can use it. So my motivating example was I want to take some data from the keyboard or a file, and I don't know how much there is. It's integers. I want to get them all into an array. So we're going to use vector because it's like a better array. So here's my function that's going to do that. Called it get integers. It takes a stream input, an input stream. So an input stream cin, which you've been using, that's its type. So this could be the standard input, the keyboard. Can actually also be a file. Okay, so that's what I'm passing in is some stream. Could be cin. And I'm going to return a vector, and it's a vector of integers. And that's going to be all the numbers that were typed in that stream. I need a temporary variable. Okay, so I need to store that locally. So I'm going to declare a variable of, and I'm going to call it integers, and it's a standard vector of integers. Okay, so the way you read this is in the standard library, I want the vector templated class, and I want you to make me a vector of integers. Okay, so far I've defined my function, what the interface to my function is, and I've made a temporary variable. Okay, oh, and I need to get at the vector templated class, so I need to include its header file, and its header file is called vector. How do I do this? It's not very long. But basically, I'm saying let's declare a variable value, and while there's still data in the stream, which again I'm going to pass C in. Example, you're going to see my main function passes C in for this. Take the next value out of it, store it in this variable value, and then add it to my vector, add it at the end. So my vector's name was, my object's name is integers, call its member function pushback, and that pushback wants to know, well, what are you putting in the vector? So what I want to put in the vector is the number I just read, value. You keep doing that, keep going around this while loop until there's no more input, and then we're done. And then we just return our vector. And it's an object. We can return it the way we always would. And we've said the type that this function returns is a standard vector of integers. That's fine. That's what I'm trying to return. It's all good. Okay? Does it all make sense? So vectors made this pretty easy to do. The code is very short. Do we need an overloaded operator for this to work? I mean, inside vector, they have overloaded operators like the square bracket operator. You don't have to do anything. I mean, the vector class, the vector templated class is already written in a standard library. So all of this just works. Okay. Let's see. Yeah, Rohan, that particular code you wrote wouldn't work with a string. So, okay. And the key thing is that we've got this pushback member function. It inserts a new element in the vector, puts it at the end of the vector. The vector will grow in order to have enough storage. So to get a little bit of experience with vectors, I'm going to have you do a breakout room exercise where you print out what is inside of a vector of integers. Okay, so inside a main function, you've got a vector of integers. It's called integers. We've already loaded it. So we just called that getIntegers function and passed in standard input. So you already got your vector. Now we want you to print it out. So what do you need? You don't need much. You need the square bracket operator, just like an array. So, and you have the size member function. So again, the size is how many entries are in the vector. And if size is 3, they would be at index 0, 1, and 2, just like an array. Okay, so I'm going to put you back in breakout rooms and give you, 4 minutes or so to try and code that up. So. Okay, welcome back, everybody. How many people were able to complete that in the time you had? Give me a sense of whether I'm giving you too long or too little time. Okay, so see a bunch of yeses, so that's great. Okay, so here's, there are lots of, your code might like slightly be different than this, but here's the code that I wrote. And it's, it's not super complicated, right? So it looks a lot like what you would do with an array. So for my index variable I, start at 0, and as long as it's not at the end of the vector, so vector, again, size means if we have 4 elements, we'll have 0, 1, 2, 3. So I want to stop when I get to size. I don't want to look at that entry and just keep incrementing, going through. I'm going to print out the value in the vector at that location, that index. So, and I get that value just with the square bracket operator like I would with an array. And that's all there is to it. Okay. Let's see. So Susan was asking, do I need to use standard cout? It's exactly the same as the discussion we had before about if you have using namespace std at the top of your file, then you can leave out this std. You'll figure out what that's cout. You'll look in the standard library and it'll see cout and use it. It's considered slightly better programming practice to be explicit and just say I want to use cout from the standard library. It'll give the same thing. Endl, if you use endl and you don't have the using namespace std, it's the same thing. Endl is actually defined in the standard library, so it's actually std : endl if you don't have the using namespace std. So you'll have a bunch of things that you've just been typing where you'll put std : in front of them, or if you go, this drives me nuts, you can do using namespace std again. Okay, let's look at how this works. So here's that same code. Well, here's the code I showed you a little while ago, the getIntegers. Okay, the getIntegers where we're reading numbers in, but we don't yet know how many numbers we have to store is the more interesting function. So we're not gonna look at the print one, we're looking at the input one. Okay, so let's say we take the same 5 numbers that a user is gonna enter. Let's see what's actually happening behind the scenes. So the first line that's interesting is this one. Okay, so we declare an object named integers, and it's of type vector of ints. We didn't put anything in the brackets after this, so we're getting the default constructor. The default constructor for a vector is going to go create this integers object, and it's an empty vector. Okay, so what does that mean that it's an empty object? Well, its size is 0. There's nothing in it. Now, inside that object, what there actually is, well, there's a member variable called size. There's actually a dynamically allocated array inside the vector. That's why this behaves so much like an array, is it actually has an array inside of it. Okay, so a dynamically allocated array is really just a pointer. Okay, so we have an int star a pointer to some storage. And vector has another member variable called capacity. And it's up to the creator of the standard library to decide what this capacity should be. It's basically how many entries can I store. Size is how many entries have I actually stored, and you use size all the time. Capacity is kind of an internal variable. You don't really need to look at this, but the vector knows how much storage it has inside of it. How big is that internal array? So the creator of the standard library can choose how to, what's the initial value of this. Commonly, this could be some small amount, maybe 3. So we've got room for 3 things, but we don't know what's in any of them. So our size is actually 0. We go through this while loop. Okay, so first time we hit this while loop, we read the number 1 and we call pushback on the number 1. And what the vector does, what this member function does, so you don't write any of this code, it just all happens for you. Size gets incremented, so we'll now have size of 1. And we store the number that was passed in, 1, in the first entry. Okay, we go through the loop again. Okay, so we're going through this while loop over and over again. We get the number 3. Okay, we increment the size again. Well, we don't do it. Vector does it when we call pushback. It increments the size to 2, and it stores this new value. So it stores 3 at the end of the vector. We go through the loop again. We get 8. Size becomes 3. We store the 8. Okay, all pretty simple so far. Now, the more interesting one is what happens when we hit number 7. We don't actually have enough storage to store 7. Inside the vector, the creator of the standard library said we'll initially have capacity 3, so we actually only have room for 3 numbers. What standard vector does is actually what Rohan said at the start of this kind of section of discussion. It's basically going to allocate more memory. So it's going to make a bigger internal array so that it has room for this. And it'll do that all for you. I'm showing you what pushback does. You don't have to do anything. This all happens. So yeah, so Suleiman is saying make capacity 6. And it's up to the creator of the standard library to decide how much to increase the capacity. But the common thing that will be done, this is what most implementations of the standard library do, is they double it. So you had room for 3 things. The pushback call will allocate with a new array with space for 6 things. Okay, it updates the capacity. Well, it basically copies over all the same old data. So we had 3 items. We don't lose those. Those all get copied over. The capacity is now 6. So pushback updates that, and it deletes this old array inside the vector, so we don't have a memory leak, and it updates the pointer inside of the vector to point to the new storage. And finally, it now has enough room, so it's going to increase the size to 4, and it's going to actually store this number 7 in the proper spot. Okay, and now we just go through again. The last number is easy, so we store the 2, we say the size is 5, and we're done. Okay, we only had 5 numbers, so we exit this loop. There's actually room for a 6th number. We don't use it. So you may have extra space at the end of your vector, but it won't be too much because vector doubles the space every single time. And you don't really care. You should never really be looking at capacity. You should only be looking at size. Capacity is like an internal parameter of the vector so that it all works properly. Okay, and then I see a few questions here. So questions is, where is vector? Well, this internal array will be created with new. So you don't really have to worry about that. Vector manages it. This is what's going on inside, but it's hidden from you, and you should be happy it's hidden. You don't really, after this talk, you can basically just forget how this works if you want. Because you don't actually have to do any of this stuff, okay? And yes, this array, there's a question from Vicky, does this get deallocated automatically? Yes, that's the purpose of a destructor. So a vector inside of it is actually allocating memory. It allocates it on the heap, like with new. When your vector is destroyed, so it goes out of scope or you call delete on the vector, depending on how you created it, the vector destructor cleans up this internal array. So it'll get rid of it. You do not worry about it, right? You don't even need to know it exists. That's the whole point of objects and classes. Let's see. So let's see if there are any other, see a bunch of questions here. See if there are any other ones here that I should address. And okay, so Constructor is asking, how does it do this from a memory perspective? And like, how does it make sure that all this memory is together? It's because it always creates it with it asks for a bigger array if it's run out of space. It doesn't make a whole bunch of arrays. It basically says, okay, my old array is not big enough. I'm going to call new with and ask for more storage, so I get a new array. Then I delete the old array and I make this pointer point at my new array. Okay, so it's always contiguous. It always works well. And then there's a good question, isn't this copying process going to be slow for a long array? And the answer is it's not bad. Okay, so that's a great question. So the reason that vector doubles capacity every time is it means that even if you're adding a lot of numbers, you call pushback 1,000,000 times, we don't grow the vector very many times. So the capacity grows by 2x usually. Again, it's up to the standard library creator, but that's the standard technique they use. So if I was pushing back 1,000,000 numbers, for example, I only need to double the capacity 20 times, right? Because that's the log base 2 of 1,000,000. So there are 20 copies, but most of them are also very short. Only the last copy is copying 500,000 numbers. All the other ones are copying much less. So when you work through the math of, well, how fast is that? We wind up with pushback has what's called average complexity of order 1. The average call to pushback, if you do a whole bunch of them, is constant time, which is very fast, so it works well. So this is a trade-off vector makes. If you call pushback to create things, you can waste a bit of storage at the end because you might have a bigger internal array than you needed, but it'll never be more than twice as big, so it's not too much. And you can get some extra copies, but you won't get that many because it was doubling every time. So you get pretty good space efficiency and pretty good time efficiency. Okay. If you really want to micro-optimize this, you can. So if you're loading a vector and you know that I'm just going to read from it for a long time now, I'm not going to actually put more elements in, I'm just going to change my existing elements. There is a function call that you can use called shrink to fit. Okay, and that will make it'll get rid of any extra capacity. It'll actually do a reallocation of the array to the exact right size, copy everything over, so there won't be any wasted memory. So if your vector is not changing size anymore, and you think it's really big, you really want to optimize it, you can use that. If you know how many elements you're going to put in the vector in advance, then you can actually have its constructor just make you a vector of the right size right away. Or you can call the function called reserve to make it the right size right away. Okay, so this is all in the C++ online resources. So you don't normally need to worry about these things, to be honest. Just using pushback and constructors, vector is going to be efficient enough. But if wasting anything on some key data structure bothers you, there are function calls so that you can kind of micromanage this and get rid of any inefficiency. Does that make sense? Let's see. There's a question: if you made a dynamically allocated 2D vector, basically does anything change? And the answer is no. You can make a vector of anything, including you can make a vector of vectors. That's perfectly fine, and it all just works the way you would expect. Okay, so let's look at the different constructors for vectors. Here's my default constructor. What that does is it makes a vector of size 0, which is what I just showed you. If you give one parameter to the constructor, you get a vector with that many elements, but you don't know what the values are. So this second call would make a vector with 10 elements, but I haven't said what's in them. This third call, where I give it 2 parameters, I make a vector with 10 elements, and in this case, they're all initialized to -1. So there's some convenient destructors. Okay, let's compare vectors to C-style arrays. So here I've got a couple of dynamically allocated arrays, right? So I make A and B, they each can store 10 integers. They're dynamically allocated because I created them with new. And then I've got a couple of vectors, V1 and V2. They also store integers, and they also start off with 10 elements because I put 10 in their constructor. So they look basically the same. The way you access elements syntactically looks identical, right? Because vector overloads this square bracket operator. So if I wanted to set entry 0 of A to 5, I would do this line. If I wanted to set entry 0 of v1 to 5, I'd write basically the same line of code. So far, they look pretty much the same. What about creating copies? So if I say A equals B, okay, A and B are both dynamically allocated arrays, they're C-style arrays. What happens? So do you like this line of code? What does it do? Type it in the chat. If you know what that does, just type it in there. I think somebody must know what this does. Yeah, it's bad. It does a shallow copy. It causes a memory leak. It basically sets the pointer A equal to the address of B. All of those are correct. So it's basically you wind up with 2 pointers pointing at the storage of B, and the memory of A was leaked. It doesn't do what you want, okay? We didn't do a proper deep copy. So write that down. What about this? So these are 2 vectors. So we haven't actually looked at that yet. What do you think it should do? The creators of the standard library are very good programmers, okay? So when you think about what it should do, assume it does something that is useful. So what do you think is going to happen when I say vector 1 equals vector 2? Is it going to do the same thing as it did for these? Yeah, it does deep copies. So it does exactly what you would hope. V1 becomes a deep copy of V2. There are no memory leaks. There are no problems. This is perfectly valid code. It's used all the time. Okay, so one example of how a vector is really a better array. Okay, now I created A and B with new. So let's say I don't do this line. Okay, that line was bad. We're not going to do that. So I created A and B with new. I have to delete them at the end or I have a memory leak. So with these C-style arrays, this is my job. With vector, with this V1 and V2 that I declared up here, should I be deleting them? Because I didn't delete them. Is that okay? So what do you think? Yeah, it's okay. They have a destructor that cleans up. Inside of them, they have dynamically allocated memory, but it's not your problem. You didn't call new, okay? If the class called new inside of itself, its destructor has to clean it up, and that's exactly what happens. So one of the things you actually want to do is you're probably right now too used to using pointers. Like you generally when people have been using C-style arrays, they use pointers a lot because they have to. With vectors, you don't have to use pointers nearly as much. So if you're creating pointers in your project in this course, think about, do I need that pointer? Or should I actually just be using a vector instead? Because sometimes people, they're so used to using C-style arrays, they just keep using pointers when they don't need to. Pointers are more difficult to work with. They don't clean up their storage, etc. Use vectors instead. Okay. Yes, that's all what I just said. Can we avoid pointers this whole course? You can probably write the project with no pointers. So, I mean, you might use some. It depends how you write your code. But you might use 0. Okay? It depends what you write. So I'm not saying you're never going to use pointers again. As a computer engineer, you need to understand them. But at the same time, they tend to lead to more programming errors. So it is not a goal to just go, I want to use as many pointers as I can. Okay, so let's talk a bit about bounds checking with vectors and a couple gotchas. Okay, so I created a vector here. I used its default constructor, so its size is 0. I I push back, so I grow the vector by 1 by putting the number -3 in. So now I got a vector of size 1. I can basically update that value using the square bracket operator. So this just means the first value in the vector has been updated to -2. Now I do something bad. I say, let's just make the next entry, index 1 equal to 5. Index 1 does not exist, okay? We only put one item in the vector. So operator square bracket lets you access values, it lets you update values, it does not create values, it does not make the vector bigger. So a very common programming error is that you go out of bounds. So this is called an out of bounds access. I tried to access something and the vector doesn't exist. It's the same as accessing something in the array that doesn't exist. Don't do it. Okay, why is this particularly bad? C++ does not check this by default. In other words, it will just try to do it, but it doesn't make sense. It's accessing memory that's outside the vector, or if this was a C-style array outside the C-style array. That might make your program crash right away if you access memory that your program doesn't own. Then the operating system will kill you. That's called a segmentation fault. That's actually good because at least you see the bug right away. But if this, wherever I'm accessing in memory, happens to still be inside my program, but it's some other variable, the operating system doesn't know that's a problem. It will happen, but your program is now doing bizarre things. This is actually overwriting some other variable. I don't know which one. Your program might run now for a long time and then go crazy. That's very hard to debug. To help you with this, we can ask C++ to turn on extra checking. So the reason C++ does not check this is C++ is built for speed. It basically produces the fastest code. Because it doesn't have to check this, it won't check this. Java always checks this, but Java is slower than C++. What we do is you can build your program multiple ways. There's you can look in NetBeans or at the command line with make. You can see that there are multiple options of how to build it. If you say you want the debug check configuration, we turn on additional checking when your code is built that will immediately catch this and throw an error. So you can find the bug faster. If your program's behaving strangely, build this debug check build and see if you've got a memory problem. It does slow your program down, so then when you're trying to pass speed tests, you don't build it this way, okay? But this gives you kind of the best of both worlds. It allows you to check it. Earlier in the class, there was a question from someone about @. There's an @ operator that works almost the same as the square bracket operator for vectors, except it always does bounds checking. So if you want, you can use that. It's a little slower, but it is safer. You don't need to use the @ operator though, because we kind of give you the best of both worlds. You can build your program with normally where it runs at maximum speed and doesn't check this, or you can build the debug check build and get the extra checking and slow down. Okay. Okay, how fast is vector? So it's very fast. It gives you efficient random access to data with this square bracket operator. Just like an array, it has order 1 complexity, and it's because it has an array inside of it. And as I showed you, it also can grow efficiently with pushback. And if you really want to micro-optimize it, you can even ask for a vector of the right size to start and avoid those internal copies. But that's not a big deal. Okay, so I'm going to do I think I'm a couple minutes over, but I'll put this will be on the recording. For those who can hang around, I'm going to do a quick demo of a couple things. Okay, so I'm just opening up a little program that I wrote and going over here to be able to compile it. Okay, so this is a little program that is not a good program. Don't write this. What does it do? So the main function just calls test_vec, and all test_vec does is it says, give me a vector with n elements all initialized to 20. Okay, so that's the constructor I'm using. N is 100. So 100 elements all initialized to 20. Then I'm going to loop through the whole vector, and actually more than the whole vector. The vector's got 100 elements, but I'm actually going to loop through 106. Okay, I should go from 0 to 99, but I'm going to from 0 to 105. And at every element, I'm just going to increase its value by its index, and then I'm going to print it out. Okay, so let's just make this program. All right, so make clean basically gets rid of any old build results, non-typing make. And make built the default configuration of this program, which basically is useful for debugging, okay? And now I'm gonna run it. Okay, so let's look at its output. So it's just printing out every entry in the vector, and the code I wrote, the first one should be 20, the next should be 21, and so on. That all looks good. Where it gets dodgy is I know this only actually has 100 entries, so 99 is the last entry that actually exists. It's got the right value. 100 does not exist, but actually I got a weird number for it. I should have gotten 120, I got 100. 101, I should have gotten 121, I got 101. 102 gives a weirder value still. 103 is a bit of a weird value. 104, 105 look really weird. My program didn't crash. I didn't get a seg fault, but the output's not correct, and it might not be obvious why. In a large program, this can be really insidious because you basically have corrupted memory. The program might not die for a really long time, and it can be really hard to find. So what I'm going to do now is I'm going to just get rid of the build results again, and I'm going to type make conf equals debug check. And you can see the options have changed. It doesn't really matter what they are, but basically the options that are being sent to G++ look more complicated now. And that's turning on this extra checking, which will slow us down, but are going to help us. Okay, so I ran the program again. My output is the same up to the 99th index, because those are the real indexes. They all look fine. As soon as I tried to access index 100, I got this error message. It says basically there's an error inside the vector. So this is telling me where I can look in the standard library. But the most important thing is it says you are trying to use index 100, which is out of bounds because the container, which is a vector, only has 100 elements. So 0 to 99 are okay, 100 is not. You tried to do a bad thing. And it tells me the address of the vector that's involved in this, in case I want to now bring it up as a debugger and start looking at what's there. And it kills my program as soon as this happens. This is way better. This is way easier to debug. So you should use the debug check build commonly. Okay, I'm going to do one more demo for people who can hang around. Let's see. And let me show you this one. Okay, so this is another, this is a speed test. So hopefully I've convinced you that vector is better than array and you should generally use it. One question you could have is, well, do I pay any speed penalty for that? And let's figure that out, okay? So here's a little program that's using vectors or arrays. I define, basically there's gonna have 10,000 elements. So here I'm making a 10,000 element vector, initializing all the values to 20. And then I go through and just do some useless computation where I go through the vector 50 times doing a computation using every element. So it doesn't really matter what the computation is. The key thing is it just does some compute that walks through a vector 50 times, and it's a pretty big vector. So let's see how fast this is. So you can time any program with the time command. So I'm going to just type time, and then the name of the program that I just built is vec versus array speed. So we'll time it. Okay, it produces a little bit of output, and then this basically says 1 minute, or sorry, 1.57 seconds. That's how long this took. It tells me a little more detail, but this is the key thing. 1.57 seconds is how long it took for this to go. Okay, so if I take this program, because vector and array both support the same square bracket operator, I can actually change this to using a C-style array. Just by commenting out the vector declaration and instead allocating a C-style array. So I just changed that code to use a C-style array. I'm going to rebuild the code and I'm going to rerun time. If I type exclamation and then the start of a command, it'll rerun that command, the matching command. So I'll just rerun that. And how fast is it? It actually took 1.2 seconds. So that's actually less than 1.57 seconds. So it looks like array is faster. But that's not the whole story. So when I built this, if you looked carefully at the options, the version I was building is what's called the debug configuration. It's suitable for debugging. Compilers can also optimize your code. Okay, optimizing your code basically means they'll reorder the order in which statements run. So, for example, here it might change the order in which some of these statements run. And it does a bunch of other optimizations, trying to keep things in registers instead of memory and so on. So that can make your code significantly faster. So I'm rebuilding, and you'll see there's this option 03, which means optimization. So I'm telling the compiler, make the code as fast as possible. It'll still get the same results, but reorder things if you have to get a faster program. So now I'm going to rerun that time command and see how fast it is. Okay, so it went from 1.2 seconds to 0.44. So it made a big difference, almost tripled the speed. So when you're trying to pass speed tests, you always want to use the release build. Now let's change this vector. Well, let's change from a C-style array back to a vector. So I just made that change, I'm running it out. And I'm using the arrow keys now. I can go back and look at old commands. I'll just rebuild it. And I'm now going to time it again. Okay, now it's 0.44 seconds. Okay, so the vector now is just as fast as the array. Okay, so what are the key lessons from this? If you care about speed, run release build. When you are using it in the debugger, build the debug build. When you're doing extra checking, use the debug check build. So you're going to flip between build types. You also do not want to compare the speed of different ideas for your program except in release build, because compiler optimizations speed up some code more than others. Vectors have member functions that you're calling. When you turn on optimization, the compiler does more work to make that fast. So it actually went from a C-style array was somewhat faster than a vector to it was a tie once I turned on optimization. And also the program sped up by 3 to 4x. So all speed testing do in release build. And vectors are basically as fast as C-style arrays. So there's no reason not to use them. And that's all I had to say today. So there's a question, do vectors support any type? Yep, they do. Well, they basically support everything, because vectors don't assume any operators, so they support any type. What version of C++ do we use? This makefile was using the 2014 version. The makefile that we give you for your projects actually is using the 2017 version. It's just I haven't updated these little sample programs to use that. So a pretty recent version, 2017. What's the difference between release and debug build? Okay, so let's go let's do make clean, okay, so if I just type make with no options, we've set it so it'll build the debug build. The difference is this. -G means put extra information in the executable program so that the debugger knows the names of your variables and so on. -O0 means do not do any compiler optimizations. And that helps you when you're using a debugger and you're stepping through your code. The code will execute in the exact order you wrote it. So you'll go through this line, then this line, then this line, and so on. Okay, so that was what happened with, so now I'm going to clean this again, and now do make conf equals release. You can also do this in NetBeans or an IDE because we expose all the build types there too. You just select them from the GUI, it's the same. All right, so what did this do? Basically what changed is we turn on this O3, okay? So O3 is optimization, and now some of these lines might actually disappear. If you were in the debugger, you might see I never went through this line because the compiler figured out it didn't need a certain variable. Certain variables you may not be able to see because the compiler figured out it could get rid of them. You might actually be single stepping through your code, and you might go from this line, you might go through this line, then back to this line. And it's because the compiler decided that'd be a little faster, and you can't tell the difference anyway. So it is harder to debug release code because some of your variables may no longer exist, and your code will execute in a different order than what you wrote, but it runs faster. It's a question from Akshat. Can compiler optimizations cause undefined behaviors if it's too aggressive? Only if there's a compiler bug. So compilers, like any program, actually do have bugs, but they're rare. They do happen when you have a big enough program. So I used to work, as I said, on Quartus, which was 17 million lines of code. We would find compiler bugs, because when you compile 17 million lines of code, you will actually find bugs. We didn't find many, and then we'd have to just go do strange things to little bits of code to not trigger the bug. You guys are very unlikely to hit a compiler bug. They are heavily tested. And what you're describing, where the compiler optimizations change the output of the program, is a bug. Let's see. And let's see, how fast is it if you want to make a static length C-style array? So creating a dynamic array involves a call to new, whereas a static array does not. So a static array, where you basically just defined a compile time, I have an array of 20 things, is a little faster because you don't call new. If you're only calling new once, though, this is a very, very small difference. You shouldn't worry about it much. But new takes a little bit of time. So if you avoided calling new, you'd save a little time. In a large program, normally your time is in your loops and things you do a lot. So if you're talking about I have a few calls to new, you will never notice, and you shouldn't worry about that. If you had calls to new and delete in some key loop that you do 10 billion times, then trying to get rid of new and delete in that key loop can speed up your program. That's kind of beyond where we go in this course. That's where you get into computer systems programming in 4th year, and maybe take that in 3rd year if you want to. That's where you get into that kind of thing, like where you're really learning how to micro-optimize a program. You're free to do it, but we don't expect that in this course. You don't yet know enough in order to do that level of micro-optimization. Let's see. Any other questions? Anyways, lots of good interaction, so thanks. It makes this a lot more interesting. I think for me and I think probably for you guys too. So thanks for all the questions. And I might have missed some because there were lots of comments in the chat. So if you've got more questions, I'll hang around, just ask them. But I'm going to stop the recording now. Yeah, so maybe I'll answer this question on the recording. So the question from Yusuf is, does vector capacity start at 3? Don't rely on that. Okay, so in some implementations of the standard library, that's what happens. It's not guaranteed because it's a detail. So I'll show you next week some good resources on the C++ standard library online, because nobody remembers all this stuff. You go to an online resource and just kind of look up what are the member functions of vector and so on. Anything that's not documented there is not guaranteed. So vector capacity starting at 3 is an implementation detail that will not be guaranteed. You should never write code that relies on that. But the truth is, you probably have to try to write code to rely on that. So just don't do that. Conductor is asking, will the future tutorials be as fast as today's? Probably next week's, yes. The ones after that, maybe not as much. We're trying to go through a lot of STL material in the first 2 weeks. Okay, thanks everybody.